Okay, so in 5-6 we talked about the hinge theorem and the converse of the hinge theorem. So the hinge theorem is the one that says if you've got two pairs of congruent sides, and the angle between one of those is larger than the angle between the other, then the side opposite the larger angle is going to be bigger than the side opposite smaller. And then the reverse of that, or the converse of that, the hinge theorem converse said that if you've got two pairs of congruent sides again, and the third side of one triangle is bigger than the third side of the other, then the angle opposite that third side is going to be bigger than the angle opposite the smaller side. So this just says complete with less than, greater than, or equal to. If you look at number 1, you've got two pairs of congruent sides, and then two angles. So when it looks for KL to NP, what's the relationship between KL and NP? KL is less than, right? 75 is less than 80. KL would be less than NP. That would be which of those? The regular hinge theorem or the converse? The hinge theorem. Good. Number 2, so you've got that 28 would match 28. You've got one pair of congruent sides. Do you have a second pair of congruent sides? Where? Good, the reflexive side. So then the third piece of information that we have is 22 and 12. Since 12 is smaller than 22, that makes angle 1, good, less than angle 2. And this one would be, which theorem? The converse, good. So if you had to explain why, the first one, when you're proving something about the sides, it's the initial hinge theorem. If you're proving something about the angles, it's the converse to the hinge theorem. Questions on either of those? All right, so definition of a midsegment is a segment that connects the midpoints of the sides of a triangle. If I were to draw this out, I would draw a triangle, draw a segment that connects the two sides at each side's midpoint. So they don't have to be equal on the left and the right. They just have to be equal where the segment hits them. So this segment is your midsegment. Who can tell me what the midsegment theorem says? Perfect. Okay, so the midsegment of a triangle is parallel to the third side and 1/2 its length. So if I'm using the diagram that's there, that means that AB equals 1/2 CD, and AB is parallel to CD. All right, so this one says sketch a rectangle whose horizontal length is 10x and vertical length is 5x. Then find the length of the diagonal and the midpoint of the diagonal. So if I had given you a coordinate grid, you always want to start at 0, 0. Horizontal would be 10x, so I've moved to the right 10x. Vertical was 5x, so I've moved up 5x. Which would make my fourth point what? Good, 10x, 5x. So I moved to the right 10x, I moved up 5x. So the diagonal, I could either draw it this way or I could draw it this way. It doesn't matter, they'd be the same. Rectangles has congruent diagonals. So if I wanted the length of one of those diagonals, how do I find length when I'm given coordinates? The distance formula. So I'm going to use the distance, I'm going to use the red one. So I'm going to use the distance formula of 0, with 0, 0, and with 10x, 5x. So distance formula, square root of x2 minus x1 squared plus y2 minus y1 squared. If this is my x1, y1, x2, y2, then I'd get 10x minus 0 squared plus 5x minus 0 squared. And I'd get 10x squared plus 5x squared, which is 100x squared plus 25x squared, which is the square root of 105x squared. Is 125 a perfect square? No, right? It would be like more than 11 squared but less than 12 squared, right? 121 and 144. So to figure out if this can be simplified, I'm going to use my factor tree. What goes into 125? 25 and 5, good. And then 25 is 5 and 5. So when we break down into our factor tree, how many of one number do we need to take to the outside? 2. So these two 5s come out to the front as 1 5, and this 5 that's left by itself will stay underneath. And then there's 2 x's, so I can bring out 1x and put it on the outside. But the catch with variables is I don't know the sign of that, so it has to be absolute value. So 5 absolute value of x times the square root of 5 is the length of my diagonal. How would I find the midpoint of a diagonal? What's the midpoint formula? Good. x1 plus x2 divided by 2. And then y1 plus y2 divided by 2. So again, it won't matter which diagonal I use, because diagonals in a rectangle are congruent and they're going to cross at the same point. So the midpoint of one is going to be the midpoint of the other. So let's say I stick with these again, and I did the zeros and the 10x. So I would do 0 plus 10x divided by 2, 0 plus 5x divided by 2. I'd get 10x divided by 2, which is 5x, and then 5x over 2, which can stay as 5 over 2x or 5x over 2. Or you could have made it, 2.5x, 2.5x, any of that would have worked. Okay, 5-2 started perpendicular bisectors. So this was the first of our 4 segments that have a definition, have a theorem, have a point of concurrency with a name, right? So this is where a lot of the vocab started. So what is a perpendicular bisector? Remember that its name kind of gives the hint, which would be what?
It's a bisector and it's perpendicular.
Okay. So can it be a line, a ray, a segment, a plane? Yeah, any of it. So it's a line, ray, segment, or plane. That is perpendicular. To a segment at its midpoint. So in this drawing, you could say line CD, you could say ray CD, you could see segment CD. Any of that is the perpendicular bisector. of segment AB. But what is bisected has to be a segment. Why? It's the only one you can find the middle of, right? I can't find the middle of a line or a ray or a plane. Who could tell me what the perpendicular bisector theorem said? Not sides. From the endpoints. Okay, good, close enough. So a perpendicular bisector, so if a point lies on the perpendicular bisector, then it is equidistant from the endpoints of that segment. So if I use the diagram that's already there, I can say that CA is congruent to CB. Or C is equidistant from A and B. What other point is equidistant from A and B? D, good. Any point that lies on that perpendicular bisector. Okay, then the perpendicular bisector theorem had a converse. So if the initial theorem says if a point lies on the perpendicular bisector, then it's equidistant from the endpoints, what does the converse say?
If a point is equidistant from a second endpoints, it lies on the perpendicular bisector.
Perfect. So if a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector of that segment. So in a case like that, we would say if AC equals CB, or if C is equidistant from A and B, then C lies on the perpendicular bisector of AB. Okay, what is a point of concurrency? Arel. Good. A point where 3 or more lines intersect. So what's the point of concurrency of perpendicular bisectors called? Circumcenter. The point of concurrency of perpendicular bisectors theorem, perpendicular bisectors of an acute triangle meet where? Inside. Of a right triangle they meet on, and an obtuse triangle outside. So perpendicular bisectors are in, on, out, depending on the triangle. And then there was a theorem called the point of concurrency of perpendicular bisectors theorem, which told you that from the point of concurrency, or from the circumcenter, to where is equidistant? To the vertices. Good. circumcenter to the vertices. Okay, 5.3 was angle bisectors. So definition of an angle bisector is what? Use its name. What does it do? It bisects an angle. What does bisect mean? Cuts it into two equal parts. Okay, so it's technically a ray. It could be a segment, it could be a line, anything like that. That cuts an angle into two congruent angles. So ray AB bisects angle CAD. And the angle bisector theorem said that if a point lies on the angle bisector, then what? Good. So what was special about the segment that connected the sides to the point on the angle bisector? What did it had to have? It had to be perpendicular. So in order to show true distance, those little segments had to be perpendicular. So if this was A, B, C, D, okay, if BD was the angle bisector of angle ABC, then D is equidistant from the sides, or DA would be congruent to DC. But again, you have to have the right angles. So angle bisector theorem says if a point lies on the angle bisector, it's equidistant from the sides. What does the converse say? Okay. Perfect. If a point is equidistant from the sides of the angle, then it lies on the angle bisector. So in that case, you still need the right angles, but you would say something like, if AB equals AD, or if A is equidistant from the sides of the angle, then CA bisects angle BCD, or CA, ray CA, is the angle bisector of BCD. Or A lies on the angle bisector of BCD. God bless you. Anything like that. What's the point of concurrency of angle bisectors called? I should give you back your quizzes. In center. And the point of concurrency of an acute triangle meet where? Inside. How about a right triangle? Inside. How about an obtuse triangle? Inside. Remember, in center is always in the center. It's always inside. And the point of concurrency of the angle bisector theorem says that from the in-center to what is equidistant? To the sides. All right, so 5-4, medians and altitudes, the last two special kinds of segments. Definition of a median. So this was not on your quiz, this has been since your quiz. What's the definition of a median? Good, angled to the midpoint. So a segment connecting vertex to the midpoint of the opposite side. So the difference between angle bisector and perpendicular bisectors is that you can have an angle bisector of an angle, it doesn't have to be inside a triangle. You can have a perpendicular bisector of a segment, it doesn't have to be inside a triangle. But a median is the median inside a triangle, and an altitude is inside a triangle. There's no median outside a triangle, right? Because there's no vertex then. Does that make sense? So these two both fall inside a triangle and not outside of it. They literally can go outside a triangle, but you can't make an altitude without a triangle. Does that make sense? Yeah. Like the altitude and the medians are the ones that have to go from vertex to something opposite of vertex. And so it has to be a triangle. Whereas I could just give you an angle and tell you to bisect it, and you can give me an angle bisector. I can give you a segment and ask you to get a perpendicular bisector. So those both have theorems that don't have anything to do with their point of concurrency, because you can have it outside of a triangle. Whereas a median and altitude only exist if you have a triangle. Does that make sense? So there's no theorems of these until you have a point of concurrency. All right, so if I actually draw a median, so I get a triangle, and then I'd go from vertex to the opposite side at its midpoint, okay? And there's three of them. There's three vertices, three opposite sides, so that means there's three in a triangle. What's the point of concurrency of a median? No. Centroid. The point of concurrency of medians of an acute triangle meet where? Inside. Right triangle. Inside. Obtuse triangle. Inside. So medians and angle bisectors are always inside. If I were to draw the other medians here, okay, there's something special about these medians, or where they meet the point of concurrency. What's that theorem tell you? It's the 2/3 one, good. So this says that the length from the vertex to the centroid is 2/3 the length of the whole median. So if I use this diagram that's here, say this is A, B, C, let's call the centroid D, and this opposite point E, then if I use that median, I would say that BD is 2/3 the length of the whole thing, which is BE. I could say that DE would be what? DE would be how much of the whole segment? 1/3. So again, from vertex to the centroid is 2/3 the length of the whole median. And then the last of the special segments was altitude. What's the definition of an altitude? Emily. Good. So a segment well, I shouldn't even say connects. A segment, whoops, daisy, that goes from the vertex that is perpendicular to the opposite side or a line containing the opposite side. Really rough drawing, just so you can get an idea, okay? So there's no midpoint on this one. There's no angle bisector. There is a point at the vertex, and then it goes opposite that vertex, and it should be a right angle where it meets. So this is the one where if I have an obtuse triangle, one altitude is going to lie completely inside, but the other two will run to the outside of my triangle. We already used center, right? Orthocenter. So the point of concurrency is orthocenter. And we just said acute would meet inside. Right meets on, and obtuse outside. So the two that have a right angle, which are your perpendicular bisector and your altitude, are the ones that are in, on, out. And then angle bisector and median are always inside. So there is no theorem with altitudes. There's nothing about where they meet to another side is congruent or 2/3. There's nothing. Okay. What's special about altitudes is that they kind of go outside a triangle or in, on, outside a triangle. So all you need to know is definition, and if it's where they meet, what's the name, which is orthocenter, and then the in, on, out. All right, and then 5.5 using inequalities in a triangle. 5.10 said what? Do you remember? It didn't have a name, but this was about the sides of the angle and the angles opposite them. Actually, I'll wait. All right, so 5.10, which again, the number's not important, but what it says is, said if the longer side, or not if, sorry. side of a triangle is opposite the largest angle. And the smallest side would be opposite what? Shortest side. The smallest angle. And I bet that's not even like word for word from what the theorem says. Okay, but this is what you need to know from it. Okay, that if I had a triangle and this side was 10 and this is 13 and this was 8. If I asked you to put the angles in order from smallest to largest in that triangle, what would be the smallest? And then the middle one, B, and then the largest. There's only one left. Good. Okay. And then the 511 was just the reverse of that. 511 said that, and I'll actually get the exact wording. So 510 says if one side of a triangle is longer than another, then the angle opposite the larger side is larger than the angle opposite the shorter side. 511 says if one angle of a triangle is larger than another, then the side opposite the larger angle is longer than the side opposite the smaller angle. No, just know how to use them.
Just be the largest angle is opposite.
Yeah, that's why I put in those words. I think that makes sense. So this time if I had A and I had B and I had C and I had 50 degrees and I had 60 degrees, what would be the first thing you'd have to figure out? The missing angle, which would be? Wait for it. Carry the 170. Good. So then if I asked you to put them in order from largest to smallest, what would be the largest side? AB is bigger than AC, which is bigger than CB. Emily? It is exactly that. Yep. All right, triangle inequality theorem that said that the sum of any two sides of a triangle has to be greater than the third side. Okay, and it cannot be equal. I can't have 3, 3, and 6. The sum of any two sides has to be greater than the length of the third side. Which then led to us figuring out that if I have two sides and I'm looking for the range of the third side of the triangle must be bigger than what of the other two sides? Bigger than the difference and less than? Good. So if I said two side lengths were 3 and 5, then my missing side has to be bigger than 2 but less than 8. All right, so we just ended at 5, 6, the bell's about to ring. So I'll finish this on the video. It's literally those last two things, the hinge theorem and the converse. All right, so the last part of chapter 5 is 5, 6, which is inequalities in two triangles. And it started with the hinge theorem. So the hinge theorem says that if two sides of one triangle are equal to two sides of a second triangle, and the angle between the first two is bigger than the angle of the second two, or between the second two, then the side opposite the first angle is bigger than the side opposite the second. So basically what this means is if I have two triangles, and this is congruent to this, and this is congruent to this, but this angle, the included angle, so it's got to be the one on the top. Let's say that this one is 60 degrees and this one is 70 degrees. So the angle opposite the smaller, sorry, the side opposite the smaller angle is going to be smaller than the side opposite the bigger angle, and vice versa. The side opposite the larger angle is going to be greater than the side opposite the smaller angle. And then there was the converse, which says the same start, so two sides of one triangle are equal to two sides of a second triangle. But this time we know the third length. So the third side of the first is longer than the third side of the second. Then the angle opposite the longer side will be bigger than the angle opposite the shorter side. So now it's as though you would know that this side is congruent to this side, and this side is congruent to this side. But then this side, let's say that this side is shorter than this side. So let's say this is 10 and this is 15. So if that information is given, then I would know that the angle opposite the shorter side, in this case angle A, would be smaller than the angle opposite the longer side, which is angle D. And vice versa. Angle D would be greater than angle A. So that's the converse of the hinge theorem. All right, so that's all the concepts in chapter 5. Hopefully that will help you with your review.